Hello, and welcome to Compadre Learn. In this brief tutorial video, we'll cover the R exercises associated with the lesson Population Dynamics. Let's begin. In this lesson, we'll cover 4 learning objectives. First, we'll explore deterministic models. Then, we'll examine asymptotic dynamics by calculating asymptotic growth, stable demographic distribution, and reproductive value. Then, we'll explore transient dynamics. We'll calculate the damping ratio, amplification, and attenuation. And finally, we'll explore stochastic models. R and RStudio are required to complete the exercises in this video. If you are unfamiliar with the software, please visit the links on your screen and familiarize yourself before continuing. We'll also use the R package popdemo, and you'll be prompted to load the package during the lesson. You can download the R code used in this lesson as an R file or a PDF directly from the website. You can also follow along on the website. Objective 1. Explore deterministic models. Deterministic models are those that have no density dependence and the population matrix is constant. It means the vital rates do not change over time from time step to time step. For Objective 1, we use a desert tortoise example model from the Mojave Desert in the United States. These data are from Doak et al. 1994, and there are 8 age and size-based stages in the model. Let's start by loading the required R package. For this video, we'll be using the R file provided on the tutorial webpage. Next, we'll load the desert tortoise data provided in the popdemo package. You can view this data by typing tort in the console window in the bottom left. The next step after loading this data is to use the project function to obtain the population projection of the desert tortoise over a number of time steps. We'll use one matrix containing a constant set of vital rates, that is, the deterministic model. Remember that projected population dynamics, that is, time series of the population size and structure over time, are obtained by multiplying the constant matrix with the initial population vector. First, we'll choose a vector at random. Now we'll project the population to 50 time steps. We'll use the argument standard.vec equals true to standardize the vector to sum to 1. This object also contains the population vectors of each time step. Here, rows represent one time step and each column represents a stage. Now let's plot the population. As you can see in the figure generated in the bottom right, at 50 time steps, our population has increased significantly. At this point, feel free to play around with the amount of time at which the model is projected, the time argument in the function above, and with your initial vector, which is the vec argument in the function above. What changes do you see when you play around with these numbers? Objective 2. Asymptotic dynamics. In the long term, a population will reach a stable state and exhibit asymptotic growth. There are 3 major measures of asymptotic dynamics, and they're described by the dominant eigendata of the matrix. Lambda, or the asymptotic population growth rate, is the dominant eigenvalue. W, which is the proportion of individuals in each life stage when in a stable demographic distribution, is the right eigenvector. And V, the reproductive value vector, is the dominant left eigenvector. We can calculate these 3 parameters by using the eigs function. Here, the SS vector refers to W, and the RV vector refers to V. Since W is the vector with the proportion of individuals in each stage once the population reaches a stable state, this vector can help us project a population that has theoretically reached stability. Let's project the tortoise population matrix using this vector. We can now plot the projected population and compare a population that has the actual ratios of life stages, that is, our random initial vector from earlier, with a population that has reached stability. Objective 3, Transient Dynamics. Before a population reaches a stable state, it goes through a series of oscillations. It declines and grows at a faster and slower rate than asymptotic growth. These are called transient dynamics. These dynamics are harder to characterize as they are sensitive to the initial demographic distribution. Let's start with standardizations. To calculate deviations from stable growth, it is necessary to standardize the data. For comparative analyses, we often standardize for overall population size because sizes of different populations in our dataset may vary. We measure transient dynamics relative to asymptotic growth because different populations with different matrices have different growth rates. The package PopDemo has two different standardizations. It standardizes the initial vector so it sums to 1, which is useful to assess the projection relative to initial population size, and that is standard.vec. Second, it scales the population matrix by lambda. This standardizes asymptotic dynamics and makes it possible to assess transient dynamics. We can plot these standardizations. In this plot, tort W uses the random vector that we created earlier, and tort PWS uses the dominant right eigenvector. In these functions, the argument standard.A, if true, scales each matrix in A by dividing all elements by the dominant eigenvalue. This standardizes asymptotic dynamics. The dominant eigenvalue of the scaled matrix is 1. This is useful for assessing transient dynamics. We can also calculate the damping ratio by using the function dr on our data. The damping ratio is the rate of convergence to a stable state. It does not tell us the time it will take for a population to converge, but how fast. The higher the damping ratio, the faster it reaches convergence. In the final part of Objective 3, we'll examine transient indices, maximum amplification, and attenuation. Comparable points at which to measure transient dynamics don't have to be at the same time of the projection. Maximum amplification and maximum attenuation describe the largest and smallest population sizes relative to long-term growth lambda. Maximum amplification and maximum attenuation can occur at any point along the projection. Some populations only have a maximum amplification because they never attenuate. Some only have a maximum attenuation because they never amplify, and some have both. If we want to compare several different population structures, then it's possible to project several simultaneously. We'll start by creating 3 vectors: a population that amplifies, a population that attenuates, and a population that does both. Then, we'll bind these with the random vector into a matrix with 3 columns. After binding them together, we'll project the model with this matrix passed to the vec argument from earlier. The final step before plotting our projections is to calculate the maximum amplification and attenuation for our vectors. Now we're ready to plot our projections. The projection labeled AMP never attenuates, so it only has a maximum amplification. At the bottom, the projection labeled ATT only attenuates, so it has no maximum amplification. Finally, the projection in the middle, labeled BTH, does both, so it has both a maximum attenuation and maximum amplification. Objective 4. Explore stochastic models. It's a big assumption to think that vital rates of populations do not change over time. Abiotic, biotic, and anthropogenic disturbances may alter survival, reproduction, and growth of an organism. To examine these processes, we'll switch our model for the 4th objective to a polar bear model from Hunter et al. 2010. This population is from southern Beaufort, USA and Canada, and the model has 6 age and reproductive status-based stages. We'll begin by loading the dataset pBear. The study by Hunter et al. Also gives us the initial population vector relative to the number of individuals in each stage. As you can observe, we have 5 different matrices for the years between 2001 and 2005, and depending on the year, the polar bear's vital rates changed. According to the study, the years 2004 and 2005 were bad years due to low summer sea ice. Now let's project. The first time we used the function project with the tortoise matrix, we only passed along one matrix to the function, and it created a deterministic projection. In this case, we're using 5 different matrices. The function will now do a stochastic projection. The object returned by the projection function is the same as for the tortoise projection. However, we can now use an extra argument for the function aseq, which determines the sequence chosen for the projection. By default, aseq equals unif. It's easy to see what the random sequence of matrices chosen is, how many matrices were used to make a projection, and what those matrices are. Finally, we can calculate long-term growth of a stochastic model by averaging per time step growth rates over a long projection time. Because stochastic models also have a random per time step growth, we can calculate its variance as well. Because our lambda is less than 1, we have a decreasing population. This is also apparent in the plot of the projection in the bottom right. This concludes our tutorial video. To find more helpful tutorials like this one, please visit compadre-db.org/learn.